In addition to a chance to show off my new laser ray box, pew, 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 I also thought it might be slightly instructive for me to show you this diagram of a person with myopia. This person's eye is too big. Maybe you could say their whole head's too big, but I know that their eye is too big, because if their eye were a little bit smaller, like right here, then they would have a focused image of whatever's over there, infinitely far away, at that location, which would then be their retina. So rather than telling them, here's the problem, you can't tell somebody to get a smaller eye. But what you can do is you can put refractive optics up in front of their eye. So here's the game. Instead of, well, smashing their eyeball, I mean, I guess that does work. It does work for a short time to smash your eyeball. What I'm planning to do is to I want to put some refractive optics in here. I want these guys not to be quite so parallel. I actually want them to be diverging a little bit so that I can move the point of convergence back to there. So I'm thinking we'll do something like this. Ooh, look at that. If we put some refractive optics right there, this is what somebody's glasses look like if they have myopia. That means that they are farsighted. Myopic vision requires, concave lenses, and therefore diverging lenses, because you're converging too much. Without it, you're converging up here. With it, you can converge right at your retina. And so for years, I wore a piece of glass in front of my face that was curved like that. Actually, mine was kind of like this, so it looked really cool. But then behind it, it was like that. So it was primarily concave. So this side was convex, and that side was really, really concave. So the net action was to diverge the rays coming into my eye. Now, that's all well and good, but I want to kind of understand how that works. So I'm going to give you an equation. Let's get some of this nonsense out of the way. I'm saying, what if your far point... Now, that means, here, I'm going to draw you a little setup that we've got right here. I've got a person's eye, and I'm going to say that the lens is 2 centimeters from their eye. And the frustrating thing is their far point is only, let's say, 3.23 meters from their eye. Like, they did that experiment that I recommended. You walk away from a wall, and when you can't focus on it anymore, if you're myopic, you'll be able to see how far you are from it, and that's what I declare to be your far point. So I'm going to call this 3.23. Obviously, there's some break in this. So this is supposed to be 3.23 meters between the eye, with the lens, etc., and your far point. So the question is, what does this lens have to do to make you be able to focus at something that's infinitely far away, even though the farthest thing you can see is at 3.23 meters from your eye? What we need to move objects that are at infinity, actually freaking at infinity. We need to move their images, boom, right smack to the far point. Now, they're not going to be as big. The necessary thing is they're not going to be as big, but we can use the thin lens equation. We say 1 over dO plus 1 over dI is 1 over dF. And I'm planning to, wait a second, where is the object? I want to see something at infinity, right? Trees, baseball, moon, things that are very far away. I want to see joy also. Joy. Whoa, that's not how you spell joy. Maybe I want to see yogurt, if yogurt's really far away. Okay, so I'm saying that the object is infinitely far away. So this equation reduces to 1 over dI is 1 over F. Oh, that's cool. Slow down. Are we saying that the focal length of this sucker, now here's the thing, the object's going to be over here at infinity. And the focal point of these suckers is negative. So we know that F is less than 1, so the distance of the image from the lens is going to be on the same side. I want to put the image right here. This is supposed to be the distance of the image. So the distance of the image is 3.23 meters minus how far your glasses are away from your face, which is 0.02 meters. Now that's awesome. That means that the distance of the image, it's going to be negative though because it's on the wrong side of this lens. The distance of the image is going to be negative 3.21 meters. All right, so here's my problem. If 1 over dI is 1 over F, then I suppose dI is F. So the focal length that you need is negative 3.21 meters. You are now an optometrist. You can go up to your friends and diagnose them and get them glasses. And in fact, they will be able to see. This stuff works. I have pissed off an optometrist or two in my day, and this is how it works. You can say, I need blah, blah, blah diopters. Wait a second, what the heck is a diopter? See, optometrists want to seem really cool, so a diopter is their own unit. A diopter is 1 over the focal length, and they call this refractive power. Wait a second, get some more room in here. Refractive power. It has nothing to do with work divided by time, but it's like the refractiveness of the lens. So remember this lens, which was very refractive, and this lens, which was less refractive. That makes sense because 1 over f, see this has got a short f. 1 over f is a bigger number for this old boy, and 1 over f is a smaller number for this guy. So that makes sense. Both of these, by the way, are positive refractiveness. This one, again, is also positive, but this guy right here has a negative refractiveness. So if we were to diagnose this guy, we would say that if you've got something like that, I'm going to take the inverse here with my TI-83 plus, and I'm going to say 1 divided by 3.21 meters. Well, that, my friends, is 1 over f is the refractive power, and it's 0.31 diopters. What a cool unit. It sounds like helicopters or something. Also, it's negative. So you go into the optometrist if you find your far point to be 3.23 meters away from your face, and you say, I'm going to need negative 0.31 diopters, and they'll be like, what? How did you know that? Well, I watched a video on the internet. Oh, okay, I'll prescribe that then. Great. You could save a lot of money too. What about though, let's do the same problem if, let's write that equation out again. The 1 over a distance of the object plus 1 over the distance of the image is 1 over the focal length. And what if I've got I actually do have a student right now, and this student has a far point that is so close. His far point is 75 centimeters. So I've got this hunk of glass in front of his face, or maybe it's something polycarbonate plastic or something, and here's his eye, and we've got rays that are coming in parallel. And you have to make them look like they're diverging so dramatically much that, let's draw some more rays so we can really see how this guy has to deal with reality. They're diverging so dramatically much that his crazy converging eye can finally cause them to form an image. And so these rays come together only with a result of this crazy divergence right here. So I digress. 2 centimeters right here in front of his face. And I'm saying I need this to look like it's at his far point. Now these rays are supposed to be coming as if they're from his far point. That's the action of this lens right here to make an image that was at infinity. The object is actually at infinity, and the image is coming from right here, his far point. And I'm saying I need his far point to be what? What did I say his far point was? 75 centimeters. So let's figure out the distance of the object is infinity, so we don't have to worry about this term right here. The distance of the image, well, the distance of the image from the lens, remember, is negative 73 centimeters. So I suppose the focal length of that lens also has to be negative 73 centimeters. Now, if optometrists were reasonable, they'd just say, I need to get a lens with negative 73 centimeter focal length, but they're not. They want diopters. So we say refractive power, and we take an inverse to make them happy, 1 over f. Then I'm going to do 1 divided by 0.73, oh, minus, remember, don't forget the minus. Insert negative sign, and I get, wow, dang, this kid has a refractive power of negative 1.37 diopters. Check out what diopters are. This is 1 over a length, and that is negative 1.37 inverse meters, which is, of course, negative 1.37 meters to the negative 1. Who's feeling fancy? Goodbye.